It's a great pleasure to have Alex Brudnyi from Calgary, who will talk about the stable rank of algebras of bounded holomorphic functions. Alex?
Okay, so thank you very much for inviting me to present this talk. So actually, my talk will be about some subject related to the computation of stable rank of algebras H infinity. So let us start here. Let us start. First of all, I will give you some basic definitions. So what is this bus stable rank? So the bus stable rank was introduced by Riemann bus in early 60s. And it can be defined as follows. So suppose we have an associative ring A with identity 1. We'll say that an element from A to the power n is unimodular if there exists another element from A to the power n, such that sum bi ai, I from 1 to n, sum of coordinates will be 1. Denote the set of all unimodular elements as un a capital. So we say that a unimodular element A is reducible if there is an element C1 and so on Cn minus 1 in A capital, such that A1 plus C1 An plus so on, so on An minus 1 plus Cn minus 1 An will be also unimodular, but just of smaller rank. Now, the stable rank by the definition will be at most n minus 1 if every unimodular element from un is reducible. And it will be, stable rank denoted as SR A capital of A is the least n minus 1 satisfying this property. Okay. So the concept of the stable rank plays an important role in some stabilization problems of algebraic theory, and it is some notion analogous to the notion of dimension in topology. However, despite a simple definition, stable rank A is often quite difficult to calculate even for relatively uncomplicated rings A capital. So I'll give you some examples here. So first, let us consider the smallest possible rank rings having stable rank 1. So the first one, suppose this is just a ring having the units, if you take just the ring of formal power series in n variables over a field, then it will be a local ring, and so it has stable rank 1. Next, the algebra of complex continuous function on the unit circle has stable rank 1. The algebra of complex analytic functions on the unit disk continues up to the boundary. This is so-called disk algebra. It has stable rank 1 as well. The algebra of all complex analytic functions on the plane has stable rank 1. The algebra, which is just the primary interest for me, just the algebra H infinity of bounded holomorphic function on the open unit disk. This algebra also has a stable rank 1. Now, example of rings having stable rank 2. For instance, the ring of integers, and I will show you how to prove it. The ring of polynomials of one variable over a field F. Any principal ideal ring which is not a Euclidean one also has a stable rank 2. Now let us show how to prove that stable rank of the ring of integer is 2. So what we need to show here, suppose that we have a triple ABC, which is unimodular, just from U3Z. So by the definition, unimodularity in this case means that the greatest common divisor of this triple is 1. This is just definition. Yeah? So from here it follows that there are some integers such that sum of these times ABC will be 1. Now we need to show that one can find D and E integers such that A plus DC and B plus CC, this pair is in U2Z, meaning that the greatest common divisor of this pair will be 1. Okay, so without loss of generality, we may assume that A, B, C are not in the set 0 and plus minus 1, because otherwise it's very easy to prove it. So let us, and multiplying by plus or minus 1, we can assume also without loss of generality that C is natural number. Let us consider the prime factorization of C. P1 to the power K1, so on, Pm to the power Km. And denote by Pm plus 1 and so on, Pm plus n, primes in the factorization of A, which are distinct from P1 and Pm. So this means that factorization of A may have some primes from P1, Pm, but plus it has something which is not in P1, in the set P1, Pm, so Pm plus 1 and so on, Pm plus n. Further, we use the Chinese remainder theorem, and using this theorem, we can find some integer number b with the tilde, such that b with the tilde just equals b modulo pi ki, where I from 1 to m, and b with the tilde equals 1 modulo pj, when g from m plus 1 to m plus n. Okay, so in particular, from the first part here, from I, we obtain that b with the tilde minus b equals e times c, right? Because it can be divided by all factors here in the factorization of c. Okay, so for some integer e. And then, moreover, let us show now that the greatest common divisor of A and B tilde equals 1. Okay. Indeed, so if it is not true, then there is a prime number, say P, which is a common divisor of A and B tilde. Right? So in particular, P will be inside of the set P1 and so on, Pm plus n, because A actually can have only one of this and one of that in the prime factorization. But actually, P cannot be one of Pj from m plus 1 to m plus n because of this fact. Sorry, because of second I. Yeah. And therefore, P should be Pi0 for some I0 between 1 and n. And therefore, if it is true, then actually P is a common divisor of A and C as well, right? Why? Because actually we are taking here just a divisor of A, and in C yeah, and we assume that actually it is a common divisor of A. Yeah. So So in particular, this implies that P divides A divides B plus EC because of this fact. And so in divides C, in particular, it divides A, B, and C all together. But this contradicts to the fact that the greatest common divisor of A, B, C is 1. So from here we obtain that this pair, A, B plus EC, will be in U2Z. So this means that stable rank of Z will be less or equal than 2. Now, why it cannot be 1? It's very simple. For instance, just take the pair 2, 5. The greatest common divisor of 2 and 5 is 1. However, we cannot obtain plus minus 1 if as a subset of 2 minus 5n for n any integer. And therefore, this means that this pair 2, 5 is irreducible or non-reducible, which shows that actually stable rank of Z cannot be 1. So it is exactly 2. So consider other examples. I just briefly mentioned. So for instance, the ring of polynomials in n variables over a field, over a real field, subset of real numbers, has stable rank n plus 1. The algebra of complex continuous functions on a Hausdorff topological space of covering dimension d has stable rank integer part of d over 2 plus 1. The algebra of holomorphic functions on a reduced state space of complex dimension d has stable rank integer part d over 2 plus 1. Many more examples can be found in a new book by Brudnyi and Rapp, which will be published soon. So Rudolf is here just as a participant of our seminar today. And if you wish, you can just ask him for the reference of their book. But the main subject of the talk is just about stable rank of the algebra of bounded holomorphic functions on Riemann surfaces. So the subject goes to the classical theorem of Sergei Treil of 1992, which states the following. So suppose we have two bounded holomorphic functions on the disk, f and g, of norms less or equal than 1, f and g. And assume that we have so-called corona condition, meaning that modulus of z plus modulus gz more or equal than delta more than 0 for all z in the disk. Then the theorem states that there is a function g capital from h infinity such that the function f plus g times g capital is invertible in h infinity. And moreover, we have the following bounds. Norm g capital in h infinity and norm f inverse, phi inverse in f infinity. In h infinity less or equal some constant c capital, which depends only on delta. So in as a very particular case, we obtain that the stable rank of h infinity is 1. Why? Because you see, this condition guarantees, together with corona theorem of Carlson, guarantees that the pair fg is unimodular. And the result of Treil says that actually this pair can be reduced to an invertible element in H infinity, which is exactly that, says that stable rank cannot be more than 2. So it will be just actually less than 2. So, and therefore it is 1. Now it was an observation of simple observation of Tolokonnikov of 1995 that actually Treil's theorem is equivalent to the fact that stable rank of the algebra H infinity d times n is 1 as well. What is it? d times n. So we have a countable union of open unit disk and consider H infinity, so bounded holomorphic functions on this countable union with supremum norm still. So this will be H infinity dm. Okay, and so stable rank will be, or this algebra will be 1. Why? Because actually, because of these estimates. We have uniform estimates for the solution. In the same paper in 1995, Tolokonnikov, using Treil's theorem and certain factorization lemma for H infinity functions, proved that the stable rank of H infinity S is 1 for finitely connected plane domains and some Berens domains, some specific Berens domains. Yes. Since then, I believe there is no other classes of Riemann surfaces for which it is known that stable rank H infinity is 1. I believe so. But maybe someone here from my listeners can give me a reference if I'm wrong here. On the other hand, for every natural number n, one can construct a Riemann surface S such that stable rank of H infinity S will be more or equal than n. Okay, so of course, in this case, for this Riemann surface, Corona's theorem is not valid anymore for H infinity. And in particular, this is why we have stable rank more than 1. Yeah. So, but in general, there is no, I don't have any ideas about stable rank of H infinity over Riemann surfaces for which the Corona theorem is true. Okay, so here just my result, which is very similar to the result of Treil now. So actually, it covers a larger class of Riemann surfaces, but I cannot have a unified definition of this class, and therefore I just choose some subclass, also very important subclass of Riemann surfaces for which the stable rank is 1 for H infinity. So let S with the prime be an unbranched covering of a finite bordered Riemann surface S. So here, when I'm saying unbranched covering, I don't assume that S prime is connected. Actually, I can take the joint union of connected unbranched coverings of a finite bordered Riemann surface, and still it will be my S prime. So assume that F and G belongs to H infinity S prime. They are of norm less or equal than 1, and they satisfy the Corona condition for some delta more than 0. Then there is a function G capital from H infinity S prime such that the function phi capital F plus G times G capital is invertible in H infinity S prime, and moreover, we have the following bound of norms of G capital and phi inverse. So all the norms are bounded by some constant C, where constant C depends only on delta and on the underlying surface S. Okay, and that's it. It does not depend on the choice of the covering, actually. So this is indeed an extension of Treil's theorem, because in the case when S prime is D, we obtain exactly the Treil's theorem for some C which depends only on delta. Okay, so first of all, I will just provide you some algebraic corollary of this fact. And then I will just sketch maybe some ideas of the proof of this theorem. So let us denote by Mn H infinity S prime, the algebra of n times n matrices with entries in H infinity S prime, will be regarded as a subspace of bounded linear operators on H infinity S prime to the power n, and equipped with the operator norm. So we can apply the previous result to the problem of reducing a matrix with entries in S, L, N, H infinity S prime. This is just a subgroup of matrices of determinant 1 to the identity matrix by addition operation. That is, representing a matrix by the product of elementary matrices. Elementary matrix is a matrix which differs from the identity matrix by at most one non-diagonal entry. Okay? So it's kind of Gaussian elimination process. The only thing we cannot multiply one row by a constant and add to another row. We can just use only addition operations. So corollary from this theorem will be the following. Every matrix from SLN H infinity S prime of norm less or equal than M capital can be presented as a product of at most n minus 1 times 3n over 2 plus 1 elementary matrices whose norms are bounded from above by a constant dependent only on this n, on the size of matrix n, and on the underlying Riemann surfaces. That's it. So the main novelty of this result is that actually we have a bound of norms here, bound of norms. Because without that, this is just the standard application of the fact that some algebra has the bus table rank 1. So if it is true, then according to some classical result due to Dennis and Wasserstein, we obtained this product with n minus 1 times 3n over 2 plus 1 matrices. I believe it just even first was proved by Wasserstein. Okay, so the novelty is just in these constants. So the product will be by matrices of bounded norms. Okay, so now just I will describe you some ideas inside the proof of this result. So for this purpose, I need to recall some definitions from the from the theory of maximal ideal space of commutative Banach algebras. So by MA, let us denote the maximal ideal space of a commutative Banach algebra A. This is a set of all non-zero homomorphism from A to the field of complex numbers. Now it is easy to see that norm of each such homomorphism is at most 1, and therefore each such homomorphism is continuous linear functional on A, and so in this case we obtain that the maximal ideal space will be a subset of the closed unit ball of the dual space A with a star. So this space will be compact Hausdorff space in the weak star topology induced by A star, which is called in this series the Gelfand topology. So let's see, MA denotes the Banach algebra of continuous complex valued functions on the maximal ideal space A equipped with supremum norm. Now, then each element A from this algebra can be thought of as a function from CMA via the Gelfand transform defined as follows. So Gelfand transform of element A computed at the homomorphism phi will be phi at A. So it's easy to see that the map, the Gelfand transform is an increasing normomorphism of Banach algebras. So it is injective if algebra is so-called semi-simple. This means that the Jacobian radical of A is trivial. So So what is Jacobian radical? In this case, it will be just intersection of all maximal ideals of algebra A. So trivial means that such intersection will be just zero. In this case, algebra is called semi-simple, and therefore the Gelfand transform will be just injection. Now, just give some details, some general result about stable ranks of Banach algebras, described in the papers of Laratonda, Horach, and Suarez. So the statement stable rank of A equals 1 can be reformulated as follows. So suppose we have an ideal in the algebra A, and denote by hull of this ideal the set of points in the maximal ideal space of A such that the Gelfand transform f x equals 0 for all f from this ideal. So in some sense, this is just the zero locus of the ideal I capital. Then the following proposition holds. The following conditions are equivalent. Stable rank of A is 1 for every ideal I in A and any continuous function from the hull I to C minus 0. So this means just non-zero continuous function f. There is a function f capital, which is continuous here, such that so forget about this for this head. So, such that f restricted to hull I equals f. So roughly speaking, this means that any non-zero continuous function on the hull can be extended. I forgot to. So here just I missed it. So can be extended to function f capital, which is also non-zero on the maximal ideal space. So I forgot to add it here. C M A with values in C star. So just f capital is non-zero as well. Okay. And therefore, the main idea, the main thing now, just in our case, we're taking some hull or some ideal continuous non-zero function on the hull. We need to know how to extend it to continuous non-zero function on the whole MA. So I need some other definitions here. So suppose we have a closed subset of the maximal ideal space A. We say that it is polynomially convex if for every point x, which is not an S, there is some element from algebra A such that maximum or S of the Gelfand transform of A strictly less than modulus of the Gelfand transform A at X. This is just a generalization of the usual polynomial convexity in the plane using holomorphic polynomials. Example, every hull I is polynomially convex subset of the maximal ideal space just by the definition, because it's zero locus of some family of functions from A capital. Moreover, it is easy to check that if you have a polynomially convex set, then the union of this polynomial convex set with any hull still will be a polynomially convex set. This is what we use in the proof. Okay, so the main technical tool which is used in the proof of the theorem about stable rank is the following fact. So let us consider any subset of natural numbers and consider this space D times F, so just disjoint union of copies of the open unit disk of cardinality F. And suppose that S will be just in the maximal ideal space of this algebra. and suppose that S is polynomially convex. Then for every continuous non-zero function from S to C star, there is a function. Okay, again, I forgot it. So there is a non-zero continuous function f on the whole maximal real space, such that its restriction to S is f. So without f, without head. Okay. So, and here again, I need just that this function is non-zero. So the difficulty here that this is just a nonlinear interpolation problem, because our function f has values not in C, but in C minus 0. And the extension also takes values in C minus 0. And this is why it is difficult to prove. Now, for the algebra H infinity, this means that cardinality of f is 1. The result was proved by Daniel Suarez in the paper of 1994, using the construction of Sergei Treil and some arguments from algebraic topology. So the general case that I proved in this year can be reduced to the result of Suarez, provided that we know something about the structure of the maximal ideal space H infinity d times f. Okay, so I know a bit more about this structure. Now I was able just to prove the general result. So this theorem we use in the following result, also of general nature. So here's just the result. So suppose that we have a connected compact Hausdorff space such that it can be covered by finitely many closed sets x1, x2, and so on, xm, and such that there are continuous maps Sg from the maximal ideal space of H infinity d times f into X. F is some subset inside of natural numbers, satisfying, first of all, each Xj belongs to the image of Sj. And moreover, Sj is 1-to-1 over Sj inverse Xj. Okay, so roughly speaking, Xj sits not only in X, but also sits inside of this maximal ideal space. And second, what is important, that for every j from 1 to m and any I outside of the set j capital, the intersection of the union xj, j belongs to j capital, with xi, and then the inverse with respect to si minus 1, is polynomially convex inside of this set. I will show you some picture later, and you will see what really we have here as these technical conditions. So in some sense, it means actually something like the space X should be two-dimensional. Now, under these conditions, we obtain the following general result. Suppose that Z is a closed subset of X, such that for every J, the set Sj minus 1Z is a hull. Okay, so again, Sj minus 1, J minus 1 will be inside of this maximal ideal space. It is a hull there. Then, and here I wrote correctly, so then for every G from the set of maps from Z to C star, there is a G tilde from set of from X to C star, such that the restriction of G tilde to Z will be G. Okay, this will be exactly what we will need actually. So the main idea just to take some partition of our covering of Riemann surface and some good subsets satisfying the conditions of the theorem, of the proposition, sorry, or this one. Where is it? Yeah, or this proposition. And then to apply this proposition to this set. Okay, so now applying to the, so we need to construct actually then this closed cover for our space X, which in our case will be the maximal real space of H infinity over the covering of a borderate Riemann. So without loss of generality, we will assume that our borderate Riemann surface S is a relatively compact subset of another open Riemann surface, R capital. It's standard. So for instance, you can take the double of S and then take some neighborhood there of S inside the double, so then it will be your R. So this is always possible. And now the following technical lemma will give us the required cover. There is a finite cover, Uj, of the closure of our finite borderate Riemann surface S by compact subsets homomorphic to closed unit disks, such that each Ui is contained in an open simply connected set Vi inside the larger Riemann surface, and such that the intersection of Vi with S will be also simply connected. Moreover, each Ui intersects with at most two other sets of the family, and each non-void intersection Ui Uj is homomorphic to closed interval 0, 1. So this result can be obtained from a Whiteheads theorem. So in this case, Whiteheads theorem for this Riemann surface closure of S says that there is some one-dimensional, some complex inside S bar and some good deformation retract of S bar on this subcomplex. Then taking this some partition of this subcomplex by interval. Some complex is just one-dimensional graph only. So taking partition of this subcomplex by intervals and taking a pre-image of such intervals, we obtain our sets Ui. Here just a specific case. In the case when we have a planar domain, it's much easier to do. Okay, so for instance, here's just our domain with two holes. So what we'll do, we'll just partite it in the following smaller closed sets. U1, U2, U3, U4, U5, U6. You see here that every one of that is just simply connected. Now U1, for U1, you can find just a little bit larger set V1 in the plane, which is still simply connected, and so that the intersection with our space S still will be simply connected. You see, it's still simply connected. Moreover, the intersection of there is intersection, it will be just the unit interval here, U2, U3 unit interval here, U2, U5 still unit interval here, U6, U5 still the unit interval here, and so on. So you see, so it's possible to do using the Whitehead theorem, and it's not difficult actually. Modular the Whitehead theorem, of course. Now, using this existing of such cover, let us show how to find sets Xi from the proposition. So let R S prime to S will be the covering map. By A capital S, I'll denote the subalgebra of functions continuous up to the boundary. Okay. Now we have such embedding homomorphism. a capital S inside H infinity S. And then because we have embedding homomorphism passing to the dual spaces, it will give us the transposition will give us the homomorphism R with the head of the maximal ideal space of H infinity S prime to the maximal ideal space of AS, A capital S. But these are just the algebra functions holomorphic inside S and continues up to the boundary. It's easy to check, and it is well known that the maximal ideal space of this algebra will be just the closure of S. So in particular, we have that R with the head maps maximal ideal space H infinity of S prime into the closure of S. Okay, just decompose this closure of S as before, like here. Yeah. And then take as our subsets xi in the proposition preimages under R with the head of this sets ui. Now, so then we need to define also maps. We need also, so this is just our xi here. We need to define also maps si or sj. Okay, how to do that? Let us denote by wi intersection of a larger set vi with s. In our case, for instance, in here it will be just this set, all this open set, a little bit larger than u1. Okay, now take the covering of this vi prime. This means that just preimage of wi prime. So preimage of wi with respect to the covering map. By the definition, because we have assumed that our wi are simply connected, then the preimage of wi with respect to R will be just by holomorphic to open unit disk times F, where F is the fiber of the unbranched covering. Yeah, because actually, because wi is simply connected by the Riemann mapping theorem, wi will be by holomorphic to the unit disk, and from here we obtain this. Okay. In particular, we obtain that algebras H infinity wi prime and H infinity d times f are isomorphic. Then by SI, we denote the following continuous map. It will be just the transpose of the composition of the restriction homomorphism H infinity S prime to H infinity y prime, and the isomorphism which maps H infinity wi prime to H infinity d times f. So restriction homomorphism means that if I'm taking function from H infinity S prime, then I can restrict it to this subset, open subset. Okay, and so this will be SI. This will be our SI. Of course, there are, so I'm not just telling you how to prove that this SI will satisfy the required properties, in particular, why it is actually one-to-one or the image of over the preimage of xi. But it is possible to do. So one proves that xi will be just inside the image si of this maximal ideal space, and si has an inverse on xi. And moreover, this is just another very important fact that the covering satisfy condition of the previous proposition. Roughly speaking, we need to have polynomial convexity. So let us consider this example. So I'm taking intersection of some U2 with the union of some other sets. Then this intersection maximum that we can obtain here, it will be 1, 2, and 3. 3 intervals. 1, 2, and 3. So the intersection consists of 3 intervals. In this situation, you see these intervals will be polynomially convex in C because of the classical result, which states that the compact subset of C is polynomially convex if its complement is connected. And here it will be just 1, 2, and 3 intervals, non-disjoint intervals, you see. So then the complement of these disjoint intervals will be connected, and therefore this union of 3 intervals will be polynomially convex in C. But then, of course, it will be polynomially convex also inside of this domain as well, right? Because subset of polynomials will be just set of polynomials, holomorphic polynomials will be just a subalgebra of H infinity in here. And using this simple argument, one obtains what I told you. Namely that if I'm taking this one, if I'm taking just some subset J from 1 to M and intersected with some xi, which is not in this index set, then preimage will be polynomially convex. That's it. So because we have this, then we can apply this proposition. So, and according to this proposition, it's easy to see that for every hull Z in H infinity S prime, and each continuous function on Z with values in C star, there is some extension G with a tilde on the maximal space H infinity S prime with values in C star, such that the restriction of Z will be G. But this is equivalent to the fact that stable rank of H infinity S prime will be 1. And yes, I remind you that what we need just to prove here. We need to prove also the following bound, uniform bound. But uniform bound can be obtained from the fact that S prime is just any unbranched covering of finite bordered Riemann surface. Okay, any unbranched covering. And therefore, actually, just existence theorem, the theorem about existence of this constant. If it does not exist, then actually I can just construct some unbranched covering of finite bordered Riemann surface for which there is no such uniformly bounded solution, which is contradiction. And therefore, from here, one obtains that there is a uniform bound here, C. That's it. Thank you for your attention. And this is the end of my talk. Now, if you have any questions, I'm happy to answer them.
Well, let's thank Alex. Good talks. Are there any questions?
Yes, Alex. This is Paul Gauthier. The notion of a stable rank is completely new to me. Is the stable rank always finite?
No. So, for instance, in one of the papers of Rudolf Rapp and Riemann Martinez, they proved that, for instance, the stable rank of the algebra of almost periodic functions on the real line has stable rank infinity.
Well, what about H infinity of an open H infinity of a Riemann surface is this a
Yeah,
stable
so
always finite?
I gave you, I don't know, sorry. This is what I can prove. Yeah, where is it?
Connected, I mean, yes.
Somewhere actually I formulated it. Here it is. So for every integer n, there is a Riemann surface whose stable rank is more or equals than n. Still, I don't know whether it is finite or not, because I can compare the stable rank with the stable rank of H infinity on the open polydisk of radius n. And because stable rank of this algebra more or equals than n, then here it will be also more or equals than n. But for multidimensional situation, it's kind of, we don't know even for Corona theorem for there, but stable rank is more complicated stuff, because somehow Corona theorem is a local notion. So it is possible just to prove it locally and then somehow glue these local solutions to obtain the global solution. So for the stable rank, it's just nonlinear interpolation problem. So it is impossible to, it's very difficult. No, it is possible, as you can see from my proof. Sometimes it is possible to glue together some solutions to obtain also some nonlinear interpolation result. But in general, it is very difficult. So more difficult than to prove Corona theorem.
Yes, thank you, Alex, thank you.
Yeah.
And how do things depend on the genus, like in this result?
Yeah, so it depends on the number of holes somehow.
Mm-hmm.
Even the plane, so it depends on the number of holes in the plane. For instance, if you consider finitely connected plane domain. If the size will be smaller and smaller, but again, this is just existence result, and therefore I don't know anything about the bound for this optimal constant. Okay.
And so the stable rank, you can also define it for non-commutative rings, right? I mean, like, I don't know.
Yeah. So
like you can take entries in the quaternions or something like this, or
yeah. So you need just only associative algebra with unity.
And so is it interesting to? Are there interesting examples kind of worked out for non-commutative rings, or?
It's kind of difficult question. So the basic result of Wasserstein just completes the stable rank of matrices over an associative ring, provided that you know the estimate for the stable ring, the estimate of stable rank for this ring. Then you can find the stable rank of matrices over this ring. It's just one of the basic results of 1971 of Wasserstein. Actually, if the size of matrix will go to infinity, then the stable rank will converge to 2. Yeah, so starting from some integer number n large enough, stable rank will be 2 for the matrices.
I see.
Yeah, but it cannot be 1, unfortunately, because in many problems we need 1, but it will be only 2, and there is a reason for that. Yeah, any other questions, please?
This is Mohammed. May I ask a question?
Yeah.
Just about, this is about Riemann surfaces. I'm just wondering, is it possible to, or not generally possible, have you seen any result on, more dimensional complex manifold?
No, this is what I told, that there is no any other results about H infinity on multidimensional complex manifolds. There are some results for, say, the generalization of the disk algebra. So this means that we are taking just A on the polydisk, say, or on the ball. Then this result is valid. The stable rank of this algebra is known, so it just follows from the general theory due to Suarez and Courage.
Right.
But for H infinity, there are only a few results. So this one, just the more general that is possible to obtain now, the ones that I presented in this lecture.
Right. Right. That was very interesting to me. Thank you.
Yeah, you're welcome. Any other question? Cool. So about Runge's theorems, actually, I just would like to advertise my talk during CMS meeting later. I didn't start to prepare it, but I have the paper, and so I will talk more about nonlinear approximation results for H infinity maps in this talk. I'll try just to present it in some simple way. But in fact, it just the general things that just I have found some method to obtain uniform estimates in many nonlinear problems, a priori uniform estimates, not just quantitative estimates, but a priori uniform estimates. And this is just this result due to Suarez, which I generalized, is one of these examples. Where is it? Here it is. So I mentioned that I forgot to write here C star. So any non-zero function from S can be extended to non-zero function on the maximal ideal space of this algebra. Okay. But you can get more. Actually, using this result, you can obtain just some other Runge type theorems for maps into some specific complex manifolds. Any other questions, please?
Right. Thank you.
Welcome.
Well,
No more questions. I believe that, yeah, so I'm really sorry that it is so difficult stuff and I cannot present it in just in some simple way because actually it is difficult, you know, so I cannot just, I didn't find any way just to present it in some simple words. So, yeah, so.
okay. So if there are no further questions, let's thank Alex again, and thanks a lot for the talk.
Thank you for inviting me. Thank you.
Thank you for speaking. Okay.
Yeah.
All right. So have a good weekend.